In the last lecture, we had introduced the principal component method. We had shown where it can be useful and how to do it basically. But what we did not do is to rigorously see how we can actually get the principal components, in the sense that the principal components are linear combination of the original variables, but the combinations are only meaningful when we get the coefficients of these combinations, the ages as we have defined before. So, what we will do in today's lecture would be to look at how we can find the coefficients. So, the A matrix or the coefficient matrix can be defined, and we can make the transformation from the x variables to the principal components y. Also be looking at some of the related results of principal components. Some of these we have already stated in the previous lecture, and some of this will be stating and proving today, and we will see how these results are important in interpretation of the principal components. Let us look at some of the relevant results of principal component method. Recall that what are the principal components? These are linear combinations of the original variables. So, we had y 1 is equal to a 1 prime x, where x is the set of original variables. That is the first principal component y 1. Y 2 is the second principal component given by a 2 prime x. So, that overall we have the principal components y as equal to a x, and A is the matrix that is unknown to us. So, once we know A, we can get from x to the principal components. Remember that A is orthogonal, and the way that we chose A is we maximize the variance of y j subject to the condition that y j prime y j is equal to 1, that is normalization, and the condition that y j prime or rather a j prime a k is equal to 0, where k is equal to 1 to j minus 1. So, when we are choosing y j, we are looking at a j, and we already have a 1, a 2, a j minus 1, and a j must be orthogonal to all of this. That is what the second condition tells us. How to do this? We will be looking at a result. Now, let us begin by assuming that sigma is the dispersion matrix of x. So, it is the variance covariance of x with the variances of x along the diagonal of sigma. Now, sigma is a positive definite matrix, and hence it has non-zero or rather non-negative eigenvalues. Suppose we order these eigenvalues and write them as lambda 1, lambda 2, lambda m, the largest being the first one and the smallest being the last one. So, these are ordered. So, you can get them in any order, but then you order them. Okay. Put them in largest one first and the smallest one last as you go down the eigenvalue table. Okay. And let p 1, p 2, p m be the corresponding eigenvectors. So, p 1 corresponds to lambda 1, p 2 corresponds to lambda 2, and so on and so forth. And we have a pair lambda j p j. This is the jth eigenvalue eigenvector pair that we have. There are several techniques by which you can get this. We will discuss that later on. But the important thing is that you remember that if the eigenvalues are distinct, then the eigenvectors would be orthogonal to each other. If the eigenvalues are not distinct, then there may be a number of eigenvectors not unique, which would correspond to a given eigenvalue, the eigenvalue which is multiplicity of greater than 1. In that case, of course, these eigenvectors would be linearly independent. And once you have a linearly independent set of vectors, you can always do an orthogonalization to get a set of orthogonal vectors. So, again as before, we can get a set of orthogonal eigenvectors even if the original eigenvectors were not so. So, again I repeat that if you have distinct eigenvalues, then you have orthogonal eigenvectors corresponding to each of them. If they are not distinct, then there would be multiplicity in certain cases, and there would be more than one eigenvector in those cases, but they can always be reduced to orthogonal eigenvectors. So, once we get this, we can get a set of m orthogonal vectors. What this result states is that the jth principal component is given by yj, which is pj prime x, where pj is the jth eigenvector. So, we get the elements of pj, which are pj1, pj2, pjm, and these act as the coefficients in the linear combination of the x's to yield yj. The variability of yj can also be shown to be equal to lambda j, which is the eigenvalue corresponding to this eigenvector. So, as far as the jth principal component is concerned, its variance is given by the j largest eigenvalue, and it's formed from the coefficients given by the corresponding eigenvector. And since the eigenvectors are orthogonal to each other, we can show that the covariance between yj and yk, the jth and the kth principal components, is equal to 0. And you know that the choices may not be unique initially, but we can always reduce this to an orthogonal set of p's. Now, the proof of the result. A very well known result is that the maximum of the quadratic form a prime sigma a by a prime a is given by lambda 1, which is the largest eigenvector. In general, if you have any positive definite matrix B, then maximum of a prime b a by a prime a is the maximum or the largest eigenvalue of B. In our case, this turns out to be what we have here, a prime sigma a by a prime a is equal to lambda 1. Now, since p1 prime p1 is equal to 1, and mind you, p1 is the eigenvector which corresponds to lambda 1, we have maximum of a prime sigma a by a prime a is equal to lambda 1, and that's p1 prime sigma p1, because those are the eigenvectors, and divided by p1 prime p1, but p1 prime p1 is 1. So, this is p1 prime sigma p1, and recall that the variance of y1 is given by a prime sigma a, and in this case a is replaced by p1. So, we get the variance as the maximum value, and that is equal to lambda 1. The first principal component has the largest variance, and that is equal to the largest eigenvalue, and the combination is given by p1 prime x. So, your y1 is p1 prime x. Similarly, for k equal to 2, 3 up to m, we can do the maximum. Of course, we do not need to do it for the last one, but in each case now a would be chosen such that it is orthogonal to the previous p1, p2, pk minus 1, and then you maximize subject to this condition. You get a prime sigma a by a prime a, maximum of that under this condition would be equal to the kth largest eigenvalue, which would be given by lambda k. Again, with a equal to pk, the variance of yk would be pk prime sigma pk, and you know that sigma pk is equal to lambda k pk. That is the usual relationship we have with its eigenvalue and eigenvector. So, if A is a matrix, lambda is its eigenvalue and x is an eigenvector, then we have the relationship that A x is equal to lambda x, and this result comes from there. And now pk prime pk is equal to 1, therefore, the variance of yk becomes simply lambda k. Similarly, if you look at covariance between yk and yl, we have pk prime sigma pl is equal to lambda k pk prime, again by the previous results, into pl, but pk and pl are orthogonal to each other, and therefore, the covariance becomes equal to 0. So, we now have the eigenvalues which gives us the variabilities of each of the principal component, and we have the eigenvectors which gives us the leads us to the linear combinations for each of the principal component. And since the eigenvalues are ordered, we have the first principal component having the maximum variability, and so on and so forth. Now, let us move to the second result. In this case, we have already stated this, that the total variability of the x's is equal to the total variability of the y. How do you prove this? Let delta be the diagonal matrix of consisting of lambda 1, lambda 2, lambda m. So, these are the eigenvalues on the diagonals, and capital P be a matrix of eigenvectors p 1, p 2, p m. Then again a standard result tells us that sigma is equal to p delta p prime. So, any matrix which is positive definite can be broken up into its eigenvector matrix, into the diagonal eigenvalue matrix, into the transpose of the eigenvector matrix. So, that is what we have here. Now, remember the trace of sigma is basically the sum of its diagonals, which are the variances. So, trace of sigma is the variances of the x's, which is the total variability. But trace of sigma is also trace of p delta p prime, and since we are looking at trace of AB is trace of BA, therefore, trace of p delta p prime is equal to trace of p prime p delta, and p prime p being orthogonal, this is I, and this is equal to trace of delta, and the sum of the diagonal elements of delta is the sum of the eigenvalues. So, the sum of the variances of x is equal to the sum of the eigenvalues, and remember that the eigenvalues gives you the variances of the y's, and therefore, this is equal to the sum of the y's. Now, how is this result important? If you look at say lambda j by lambda 1 plus lambda 2 plus lambda m, then this gives you the proportion of total population variance due to the jth principal component. So, you have lambda j on top, which actually is the variance of yj, and you have the total variability. You can write it in terms of lambda, you can also write it in terms of the xj's, because this would be equal. Now, if you take the cumulation of this for the first say j principal component, so that would be lambda 1 plus lambda 2 plus etc. up to lambda j divided by lambda 1 plus lambda 2 up to lambda m. That would give us the total variability, which would be obtained by looking at the first j principal component. The first j principal component, if it explains maybe 90% or 95% of the total variability, then we only take the first j principal components and stop. So, by looking at this cumulative proportion of total variability, we can come to a judgment as to how much of the variability we should retain. Let us have a very quick look at what we get from result 1 and result 2. Result 2 tells us how many principal components to retain, so that we have enough information garnered from the x's, and result 1 tells us what these principal components are and what the corresponding variabilities are. So, together these two gives us how the principal components can be obtained and how they can be used. So, these are two major results that we have. We have a third result that we can look at, which may be interesting. Now, we have y1 is equal to p1 prime x, y2 is equal to p2 prime x, etc. These are the principal components. Then, if you look at the correlation between the jth principal component and the ith variable, that is given by p j I into square root of lambda j divided by the square root of sigma ii. Basically, sigma ii is the variance of the ith variable, that is variance of xi. And what does this result actually tells us? It tells us the impact of the ith variable on the jth principal component. So, mind you, the jth principal component is composed of all the m variables, original variables. So, what does individually each of these variables have on the given principal component? How does they affect the given principal component? Some of them may have a larger effect, some of them may have a smaller effect. As we saw in the last class, that we had 5 variables, and the first principal component was composed of 2 of the variables. I think it was protein and carbohydrates, and this is how basically, as we saw in the last class, that there were 5 variables and the principal component, first principal component came out as a function of 2 of the variables, whereas the second one came out as a function of 3 of the variables. So, some of the variables do not occur in all the principal components, some of them occur in a larger way, in the sense that they have a larger influence, and this influence can be measured by this correlation values here. How do you prove this? Let us take EI as unit vector with 1 in the ith place and 0 elsewhere, so that I can write xi as EI prime x, and we can write covariance between xi and yj as covariance between, remember xi we have just written as EI prime x, so it is covariance between EI prime x and Pj prime x, that this is equal to EI prime sigma Pj. Now, sigma Pj, remember, is lambda j Pj. Therefore, this covariance can be written as AI prime lambda j Pj, and if you take lambda j out, it becomes EI prime into Pj. And what is EI prime? It just has one single non-zero element, so it will be picking up the ith element of Ej, which is Eji. So, now we have the covariance, and similarly we can get the variance of yi as lambda I and the variance of xi as sigma ii. So, the correlation between yj and xi is covariance yj by yj xi by square root of variance of yj into square root of variance of xi, and that is given by lambda j into Eji divided by square root of lambda j square root of sigma ii, and that leads us to the correlation. Again, this correlation gives us the relationship between each of the variables with the corresponding principal component and helps us to identify how the principal components are formed. This is not important as far as compiling or building the model is concerned, getting the principal components is concerned, getting the number of variables is concerned. Those are done by the first 2 results, but this helps us to interpret the results. It tells us which of the variables are more important in explaining the total variability, because once it comes into the major principal component, these variables major role in explaining that particular principal component and hence explaining the large chunk of the variability of the original x's. So, that way this results can be used to interpret the results we have from the principal components. In today's module, we had been looking at the general principal component model, the m variable model, and we saw that how we can choose the principal components by choosing appropriately the coefficients of the linear combinations. We saw that these coefficients basically relate to the eigenvectors corresponding to the eigenvalues of the sigma matrix, and we also saw that the variances are given by the eigenvalues. So, once we get the eigenvalues and the eigenvectors, we both get the proportion of variability explained by each of the principal components as well as the linear combinations themselves. And we have also looked at some of the related results. We have seen how the total variability of the original variables and the principal components are related. We have also seen the covariances between a principal component and one of the variables, so that this gives us the amount of or the effect of a particular variable on a particular principal component. In subsequent classes, we will be looking at the sample principal components and we will be looking at still further results.